Good afternoon to all of you. First of all, I want to introduce myself. Myself Ankit Acharya, working as an assistant professor in mathematics in Hasmukh Goswami College of Engineering, which is located at Vahelal, Naroda, Dehgaam Highway. Today my topic is linear transformations. So this is the topic, which is a subject of vector calculus and linear algebra. And today's my content is, first of all, introduction to linear transformations and some types of linear transformations. Let's see first of all. So this is the definition of linear transformation. Let's see what is the definition. Let V and W be two real vector spaces. So it satisfied all the conditions of real vector spaces, and a function t from V to W is said to be a linear transformation if these two conditions are satisfied. The first one is t of u plus v is equal to t of u plus t of v. This is true for all uv belongs to vector space V. And the second condition is t of k into u is equal to k into t of u. This condition is also satisfied for all u belongs to V, where and k is any scalar. So normally we are taking k as a real number. Now if domain and codomain both are same, that means our transformation t from V to V, then in that case we can say that it's linear operator instead of linear transformation, because domain and codomain both are same. So in that case we say that it is linear operator. So this is the definition of linear transformation. Let's see next slide. We see some important transformations. First one is zero transformation. How we define it is the transformation t from vector space V to W defined as t of V is equal to theta. For this is true for all V belongs to V, is called zero transformation, where theta is a zero vector in W. So this is a zero transformation. Next is a identity operator. Why it is called identity operator? I already told you that domain and codomain both are same. So that's why it is called operator. So this is identity operator, and how it is defined? Identity operator defined from V to V is I of V is equal to V. That means image of the vector V is itself, and this is true for all V belongs to V, is called identity operator. Next one is dilation and contraction operator. How we define it is t from V to V defined as t of V is equal to k into V. We know that k is a scalar. This is true for all V belongs to V, is called dilation if k is greater than 1, and it's called contraction on V if k is between 0 and 1. So if k is greater than 1, it is called dilation, and if k is greater than 1, if k is between 0 and 1, it is called contraction. So this is some important transformation, that is zero transformation. We first one see that zero transformation, identity operator, and this is dilation and contraction operator. Now next linear transformation, we normally linear transformation from Rn to Rm. So how we define? So we already seen the definition of linear transformation, but in that case if domain is equal to Rn and codomain, which is W, that is equal to Rm, then t from Rn to Rm is called linear transformation from Rn to Rm. So if domain is equal to Rn and codomain is equal to Rm, then it is the transformation t from Rn to Rm is called linear transformation from Rn to Rm. Now next question arises in our mind, that how we define the transformation t from Rn to Rm. So here is the solution. We take m real valued functions. First one is f1, x1, x2, x3 up to xn is equal to w1, f2 x1 x2 x3 up to xn is equal to w2 up to fm x1 x2 x3 up to xn is equal to wm. So total m number of real valued function whose image is a real number, w1 w2 wm. Now this m equations assigns a unique point w1 w2 wm, because we know that if we define a function, that is, we know that we already study in a lower standard that if we define a function, each point in a domain, there exists a unique point in codomain. So that's why we define like this. So that is very important. So this m equations assigns a unique point w1 w2 up to wm in Rm to each point x1 x2 up to xn in Rn. Okay, so to become a function, it's not a deal that one point has a unique value in codomain. So thus define a transformation from Rn to Rm as t of x1 x2 x3 up to xn is equal to w1 w2 up to wm. Now next question arises in our mind that when we say that a transformation t from Rn to Rm become a linear transformation. So here is a answer. If t from Rn to Rm, which is defined as I told you that t of x1 x2 up to xn is equal to w1 w2 up to wm, is linear if w1 w2 up to wm are linear, that means coordinates of the vector, coordinates of the right side, each coordinate w1 w2 up to wm are linear. In that case we can say that the transformation, this transformation t from Rn to Rm become a linear transformation. And if this transformation t from Rn to Rm defined is a linear, so it can be defined by the equation of the form w1 can be expressed as a linear combination of x1 x2 up to xn. So we are taking constant, so w1 is equal to a11 x1 plus a12 x2 up to a1n xn. Similarly w2 can be expressed is equal to a21 x1 plus a22 x2 plus up to plus a2n xn, where each aij, that are a11 a12 a1n a21 a22 a2n all are constants, real numbers. And wm is also can be expressed as am1 x1 plus am2 x2 plus up to amn xn. So these are total m coordinates, and m coordinates we can express as a linear combination of x1 x2 up to xn. So using this equations we can define or we can express in matrix notation. So in matrix notation, left side is m cross 1 matrix, because there are m number of row and one column. So w1 w2 wm, there is only one column, w1 w2 up to wm is equal to, there is m cross n matrix, a11 a12, first row is a11 a12 up to a1n, second row is a21 a22 up to a2n, and the last row mth row is am1 am2 up to amn, into again n cross 1 matrix, that is n number of row and one column, that is x1 x2 up to xn. So we generalize these notations, capital W is equal to capital A into capital X. So this is actually our standard matrix, and mind it that how we define this standard matrix using these equations. We take first coordinate of the right side and linear combination. What is the linear combination of x1 x2 up to xn? What is the coefficient of x1 x2 up to xn? a11 a12 up to a1n. So that is the first row of this standard matrix, a11 a12 up to a1n. Let's see next slide. Okay, and again, what is the second matrix, second equation? W2 can be expressed as x1 x2 up to xn. So what is the coefficient of x1 x2 up to xn? a21 a22 up to a2n. So that is the second row of a21 a22 up to a2n. This matrix, the given matrix, is called standard matrix, and how we define, how we denotate by with this notation in box TA. Sometime it is called capital A and sometime it is called just a inbox capital T. So let's solve some important example. that the given transformation are linear or not. First one is T from V to R, where V is an inner product space and T of U is equal to norm U. Mind it, V is an inner product space, so it is satisfied all the four conditions of the inner product space, right? So that you have to remember that all the four conditions of inner product space. T of U is equal to norm U. Now question is it linear transformation or not? And the answer is no. This is not a linear transformation. Why it is not linear transformation? Because to become a linear transformation, we know the definition. The first condition is T of U plus V is equal to T of U plus T of V. But in that case, norm U plus left hand side we have norm U plus V, and right hand side we have norm U plus norm V. But these two are not equal. That we know. Why it is not equal? I don't give you here example, but if we take one simple example, that if we take 1 0 with Euclidean inner product, just a minute, with Euclidean inner product, if we take U is equal to 1 0 and V is equal to 0 1, so what is norm U? Norm U is equal to under root 1 square plus 0 square, and norm V is equal to under root 0 square plus 1 square. Both are 1. But what is U plus V? U plus V is 1 1. So norm U plus V is what? Under root 1 square plus 1 square. So that is under root 2. So clearly the addition of this 2 is 1 plus 1 2, which is right hand side, and left hand side we have root 2. So clearly these two are not equal. Okay, so using one simple example we can prove that norm U plus V is not equal to norm U plus norm V. Now next example, the transformation T is set of M cross N matrix to set of N cross M matrix, where T of A is equal to A transpose. The given transformation is a linear transformation. Why it is a linear transformation? Because this is satisfied both two conditions, T of A plus B is equal to A plus B transpose, and we know the properties of transpose, that is A plus B transpose is equal to A transpose plus B transpose, and A transpose is T of A, B transpose is equal to T of B. So T of A plus T of B. So we prove first condition, and second condition is T of K into A, where K is a scalar, so that is equal to K into A transpose. K is a scalar, so we can drop it outside from the bracket. So K into A transpose is equal to K into transpose of A. Let's take another example that is also a good example. The transformation T from set of N cross N matrix to R. Why here we take set of N cross N matrix? Because where transformation is T of A is equal to determinant of A, and determinant we only define when our matrix is a square matrix. So that's why we take here domain is a set of N cross N matrix, right? Otherwise we cannot define a determinant. If number of row and number of column are not same, we know that we cannot define a determinant. So the answer is this is not a linear transformation, because T of A plus B, we know that using this definition T of A plus B is equal to determinant of A plus B, that is not equal to determinant of A plus determinant of B, which is T of A plus T of B. Now the question arises again in our mind that why these two are not equal. Determinant of A plus B is not equal to determinant of A plus determinant of B. We can give you another example. Let's see. If we take A is equal to 1 0 0 0 and B is equal to 0 0 0 1, so in that case determinant of A clearly 0, determinant of B is also 0, but what is A plus B? A plus B is equal to 1 0 0 1. So determinant of A plus B is equal to 1. So clearly determinant of A plus determinant of B is 0 plus 0 0, and determinant of A plus B is equal to 1. So clearly these two are not equal in general. So we prove that determinant of A plus B is not equal to determinant of A plus determinant of B. So the first condition is dropped, right, of linear to become a linear transformation. So this is not a linear transformation. Now let's see next example. T from R4 to R3 defined by the equation x1 x2 x3 x4. T of x1 x2 x3 x4 is equal to 2x1 minus 3x2 plus x3 minus 5x4. That is the first coordinate. Second coordinate is 4x1 plus x2 minus 2x3 plus x4, and the third coordinate is 5x1 minus x2 plus 4x3. So first coordinate is w1, second coordinate is w2, and the third coordinate is w3. Now how we make this standard matrix? I already told you that take it first coordinate. Now what is the first coordinate? 2x1 minus 3x2 plus x3 minus 5x4, and the coefficient of x1 x2 x3 x4 in the first coordinate, which is our first row of the standard matrix. So what is the coefficient of first coordinate? 2. The coefficient of x1 is 2, the coefficient of x2 is minus 3, the coefficient of x3 is 1, and the coefficient of x4 is minus 5. So that is 2 minus 3 1 minus 5, 2 minus 3 1 minus 5, which is first row of our standard matrix. Similarly, if we take second coordinate, what is our second coordinate?